Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor IARE Hyderabad. In this video, we will see deflection of open section beam. In this video, we will see the two topics. First, we will see the deflection of open section beams, and then we will see the thin-walled rectangular section beam subjected to torsion. So first here, deflection we will see, and after that, we will see the concept of torsion. So let's start with the deflection of open section beam. So bending, shear and torsional deflection of thin-walled beams are readily obtained by application of unit load method. So what we are doing, by a unit load method, we can find deflection, shear force and the torsional deflection. What is there? That by unit load method. So what is that unit load method? And in that already we had seen in the mechanics of solid also, and in aerospace, even in first module also. So like if suppose uniformly load is there, right, UDL is the uniformly load distributed, then also we are considering what this load is acting at the midpoint of this total span, right? So if suppose this is W, per unit length, so WL, then this will be WL into L by 2, that this point load will act here, right? So same way, even whatever the even UVL is there, UDL is there, or point load is there, what we are doing first, we are assuming that is acting at the point load, that unit load method, and then we are just finding the deflection because of that one. So now what happens? So we will use here again unit load method. The displacement in a given direction due to torsion is given directly by, so the displacement, that is delta, and T stands for torsion. So delta T is equals to what? Integral T naught T1 by Gj into dz. So torsion at 0 and torsion by unit load, right, by Gj, where G is the torsion constant, depends on the type of beam under consideration. So which type of beam we are considering, according to that the J value will be there. So now expression for bending and shear displacement of unsymmetrical thin-walled beam may also be determined by the unit load. So see, by unit load method what we can do, even that unsymmetrical thin wall is there, for that also we can find. Symmetrical easily we can find, but if unsymmetrical is there, then also we can use the unit load method and we can find the displacement. They are complex for general case and are most easily derived from first principle by considering the complementary energy of the elastic body in terms of stress and stress rather than load and displacement. So now what we will do, by unit load, instead of considering load and displacement, what we are using stresses and strain. So what is a stress? Load per unit area. Strain is displacement or delta L by L. So instead of considering load and displacement, here we will consider stress and strain, which already we had seen in complementary energy equation. In that we used only stress and stress instead of load and displacement. So here also by that we can use it. We observed that the theorem of principle of stationary value of the total complementary energy of an elastic system is equivalent to the application of principle of virtual work, where virtual force acts through real displacement. So just here, from the principle of the stationary value, the total complementary energy, what we had seen in the second part of the triangle, of an elastic system is equivalent to the, so means total complementary energy system is equivalent to what? Application of the principle of virtual work. So how much virtual work is there? That will be the total complementary energy, where virtual force is the virtual work is there, means definitely some force will be there, because of force only the work will be there. So virtual force means there, virtual work, so virtual force into the displacement. So the force will be virtual, but displacement will be real. So just say virtual force acts through real displacement. Some virtual force will be there, because of that some displacement will be there. That virtual force and displacement give you the virtual work. And same thing later we can just remove, because it's a virtual force. So after getting that one, we can remove the virtual forces later. So we may therefore specify that in our expression for total complementary energy, the displacement are the actual displacement produced by the applied load, while the virtual force system is the unit load. So here means what? Whatever the displacement will be there, that will be the actual displacement, Okay, because of the applied load, and the virtual force will be what? The unit load. Okay, so now considering deflection due to bending, the increment in total complementary energy, okay, due to application of virtual load is. So now what happened? Deflection. So that deflection will be equals to the increment in total complementary energy due to application of virtual load. So what will be there? Closed integral of A, this entire area. So this is the whole integral of L. Okay, from here. So first, and then integral of closed area of A, sigma z into sigma z comma 1, epsilon z comma 0, and into dA. So just simply sigma and epsilon. So where that shows the point. What is that? So yeah, into dz. So this you have to integrate, and plus moment, that displacement delta, that displacement because of the moment. Again here one stands for the unit load method, where sigma z1, that this term is the direct bending stresses at any point in the beam cross section corresponding to the unit load. So here one stand for the unit load. Epsilon, that is the strain, z comma 0, epsilon z comma 0 is the strain at the point produced by the actual loading. So 0 here is for actual loading and 1 for what? The unit load method. So similarly here 1 delta m is displacement because of the unit load. Okay, displacement for unit load because of the moment, that is this one. So this will be the overall equation of what? Deflection equation due to bending. Further, delta m is the actual displacement due to bending at the point of application and in the direction of unit load. So where it will be there? The actual displacement due to bending at the point of application where we are applying that moment or where we are applying the force. Okay, and in the direction of unit load. So the point will be where it's acting, that, and the direction will be along the direction of unit load. In which direction unit load is acting, in the same direction delta m will be there. Since the system is in equilibrium under the action of unit load, means what? System should be equilibrium even after applying the unit load, right? So that's whatever is there, that equal to 0. The above expression must equal to 0. So now this expression will be equals to what? For equilibrium, this must be equals to 0. Then only the body will be in equilibrium. Now what happened? Take this whole thing, right, to this side. Then what we can write? That 1 delta m is equals to what? This whole thing is minus, so that become plus integral of L, then integral of A, sigma z comma 1, epsilon naught z comma 0 into dA, and then whole dz, right? So this will be the delta, the displacement formula. So just see here that this delta m equals to, that's just for 1 is here because of the unit load. So L A sigma z comma 1, epsilon z comma 0, that sigma z comma 1 that represent for sigma z for unit load, and epsilon 0 because of the actual loading into dA, and then whole integral. Now just substitute the value here, sigma z, okay, and then put and sigma z and epsilon z, that's all. So what is epsilon? Sigma, that from the Hooke's law. So sigma is directly proportional to epsilon, right? So for proportionality constant, what we are doing? Sigma equals to E, that Young's modulus of elasticity, into epsilon. So from here what we can write? Epsilon is what? 1 by E into sigma. So once we have sigma, we can put that one, and we will get, just divide by E, we will get epsilon z comma 0. So for epsilon z comma 0, what we required? Sigma z comma 0, that is required. Okay, so let's find sigma z1. So first sigma z1 in terms of, already this equation we had seen for x-axis and y. So in terms of moment, this time is there. Earlier we had seen moment as well as load. So here now in terms of moment. So for finding, so my, 1 stands for again unit, right? My comma 1 ixx minus mx comma 1 ixy by ixx iyy. So here there is no confusion. This one, this remains same, only the moment about what we are taking, just to distinguish that one, this 1 and 0 is used. So don't get confused with what is 1, what is the 1 stands for the unit load and 0 is for the actual load. So instead of writing 0 unit load anything, just simply it's representing by 1 and 0. Okay, so now into with x term, so into x. Now here m x comma 1 I y minus m y comma 1. So now here in this case it's for unit load only, because we are finding for stress because of the what? Unit load, right? So everything will be for unit load. When we will find a strain for actual load, everywhere actual load is there. So just if you remember one, you can find for all. So how? So let's see, after that x m x comma 1 I y minus m y comma 1 I x y by I x x into I y y minus I square x y whole multiplied by y. So this is sigma z1. Now just see here in this and this one, I already showed you that epsilon is what? Sigma by E. So if this divided by E, then that will be the sigma, right? But here we found for sigma z1. But now what we require? To find epsilon z0. For that also I told you that we required sigma z0. So here is the sigma z0, means just replace here in this equation wherever the 1 is there to 0. Equation will be same, just we have to apply that point at where the moment is acting. So my comma 0, why? Just see, at whatever the distance is there, suppose here, this is unit load, so 1, and here actual load is acting, so 0. Now you are taking moment from here, right? So this into this distance, for m1 will be there, but for m0, this, that load into this distance, so that value will be different. So once we will put the numerical value, that time this will be different. But here just to representing where 1 is there, what is 1, what is 0, means at about what moment you have to find. So now my comma 0 ixx minus mx comma 0 ixy by ixx into iyy minus I square xy into x. So this will be the x part, plus mx comma 0 into iyy minus my comma 0 into ixy by ixx iyy minus I square xy into y. So this will be what? Epsilon z0. Okay, now just see here its method, where the suffixes 1 and 0 refers to the in unit load that I told you, that, and 0 is the actual loading system, right? So 1 is for unit load. So this sigma z1 we found for unit load, and here this we found for what? Actual loading. And now just substitute these two value here in the equation of displacement, the displacement equation, and xy are the coordinates of any point in the cross section refer to the centroidal system of axis. So centroidal system, just x-axis, like a moment of inertia along x-axis, y-axis. So that's why in xy plane, that's why here it is given centroidal system of axis. Now substituting sigma z1 and epsilon z1 z comma 0 in the moment equation. So after substituting here, delta m equals to 1 by E into Ixx Iyy minus I square xy whole square, because after that in denominator you just see here this, yeah, because this into this will get multiplied. So this part, okay. So this part whole into will be this whole part, this whole thing. So now what happened? From here one term we can take common because both this term is there. From here also we can take, after multiplying, term common. So finally what we can take common? Whole square of that one. That is here. This whole square is common. For L integral. So now whatever the part is left, just multiply. So first this will get my comma 1 will get multiplied with, just here, my comma 1. This term will get multiplied with what? This term and this term. So this into this, that numerator part, because already this denominator we have taken common. So now no need to bother about the denominator, only numerator part. So this part will get multiplied by this one and this one. So this into this one, this into this one, right? So we will get two term, this then multiplied by this one. Similarly, next step we will multiply with this whole thing to this whole thing, 1, and then again this whole thing to this here. So now for my comma 1 these two will be there. Similarly, x comma 1, these two multiplication is required. Right. So now just see here. For my comma 1, first term multiplied here. Then here, and the second one is my comma 1. Right. This into multiplied by the second term of this equation. Similarly, for x comma 1 will be multiplied by first x0, and then here x comma 1 will be multiplied by m comma 0. So overall, this will be there. Once you will just expand, substitute the values, right, and simplify, what you will get the answer. So let's see here. For a section having either x or y axis as an axis of symmetry, either any one is there, either x or y. By the time what happened, ixy will be 0. So put ixy will be 0 here. So now what happened, this term also will be 0, right? Ixy. So means this term will be 0, right? So here it's multiplied. So this ixy, so this term will be 0, then ixy, this term will be 0, ixy, this term 0, 0. So I'm just removing ixy term, right? So ixy, and this whole thing will be 0 because here ixy is there. So this whole thing will be 0, right? Now let's see how many terms are left. Mx comma 1 iyy, right? And my comma 1 ixx, mx comma 1 iyy, and here my comma 1 ixx into, so this term multiplied by iyy, this term multiplied by ixx, right? This term multiplied by ixy, and this term multiplied by this whole, this z, for that we have to find. So now this z will be there. After simplifying, what we will get, because why? Once we will multiply this one, this part get 0. Now we have ixx and iyy. So this term, when it's multiplied with square of this one, then what happen? Ixx will get cancelled. Similarly, for the second term, iyy will get cancelled and ixx will be there. So now delta m will be equals to this one, just after simplifying, expanding and simplifying. Okay, so I explained also how to simplify. So instead of first multiplying, that's why I just kept here like this, instead of the expanding the whole thing. If you will expand the whole thing, just see how many terms are here. So first, with these two, you have to multiply separately these two. So from first, all 4. For this, all 4. So 8. For this, all 4. 12. This 16. So total 16 term will be there. Then you have to multiply, simplify. So instead of that, keep in pair that 1, 1, and right. Then just put the value of ixy 0, and then it becomes shorter. Then just expand and solve. So finally, you will get that delta m equals to 1 by integral of L my comma 1 into my comma 0 by ixx, sorry, iyy. So when y is there, that time iyy. Okay. For m, similarly plus mx comma 1 into mx comma 0 by I. So x comma 1, so ixx. Like that you can remember the formula what finally you have to derive. The derivation of an expression for the shear deflection of thin walled section by the unit load method is achieved in a similar manner. So the derivation of expression for the shear deflection of thin walled section by the unit load method can be achieved in the same way. By comparing moment equation, we deduce that the deflection, that delta S, due to shear of a, so here this S stands for this time shear, then M was there, so because of moment, then that bending moment, due to shear of a thin walled open section or closed section beam of thickness T is given by just same like that was sigma. So here stress, so that sigma M epsilon 0, right? So sigma, that tau M, the tau 1 and epsilon 0. So here gamma 0 T D S into dz. So T D S is here, that dA in that case, right? So here dA. Sigma z1 is your tau 1, that sigma z is tau, epsilon z is gamma. So 1, 0. So same way, just put the values and that's all. Where tau 1 is the shear stress and an arbitrary point S around the section produced by a unit load. So again, 1 stands for unit load, 0 stands for the actual load. So a load applied at the point in the direction delta S. And gamma naught is the shear strain at the arbitrary point that where we are considering corresponding to the actual loading system. So whatever with the naught is there, that is for actual. If gamma naught is there, means strain in act because of the actual loading. And if 1 is there, so the tau 1 is the shear stress because of the unit load. The integral in parenthesis is taken over all the wall of the beam. So now this part is what? This integral is just here section. So overall the part should be there. In fact, both the applied and unit shear load must act through the shear center. So these with what? Whatever the applied load is there and the unit load is there, that must act at the shear center of cross section. Otherwise what happen? Some torsion will be there, that will get twist. So the otherwise the additional torsional displacement occur. Then we have to consider that also. So just to ignore what we are assuming, earlier also we had seen, we are assuming that force is acting at the shear center. So there is no torsional displacement, or there is no torsion experienced by that beam. So now where shear load act at the other, when shear load, so if shear load is acting at some other place, then what happened? Instead of shear center is no additional torque, that's fine. But if other than the shear center is some displacement, torque will be there. So what happened to that one? So just see, when shear load act at other point, these must be replaced by shear load at the shear center plus a torque. So now what happened if suppose this is there? Okay, load is acting instead of here, load is acting somewhere here. Okay, then replace this, put here, right, that load, and at the same point just add one moment, right, that torque. Okay, so that's the shear load and as well as the torque will act here, but that must be at the shear center only. If it's not at shear center, then we have to resolve, and then we will put both shear load and torque at the shear center. The thickness T is the actual skin thickness and may vary around the cross section, but is assumed to be constant along the length of the beam. Rewriting above equation in terms of shear flow Q1 and Q2. So again, now that was for what? This is for in terms of shear stress, shear strain. Now before that we had seen moment, bending moment. Now this is for shear stress. So shear flow Q1 is because of the unit load, Q0 is because of the what? Actual loading. So now delta S, so displacement because of the shear force will be what? Entire for L. Again this whole for the whole section, Q0 Q1 by GT into DS into DZ. Okay, so this will be the displacement. Where again the suffixes refer to the actual and unit loading system. Means again one is what? Unit load and 0 is the actual load. In the cases of both open and closed section beam, the general expression for shear flow are long and are best evaluated before substituting in above equation. So before substituting, first what happened? First evaluate separately and then substitute back here to get the best result. Okay, so what will be the best result? So just see, for an open section beam comprising boom and walls of direct stress carrying thickness TD, we have what? So Q0. So here we are taking that Q0 value is everywhere, not will be there. So same, sorry. So Sx, comma 0 because Q0 is there. So this we are just finding for the shear strain. Similarly for this one for the actual loading. So Sx, comma 0 Ixx minus Sy, comma 0 Ixy divided by Ixx Iyy minus I square xy into this after taking common, right? Then close integral of TD, that thickness, that when total span is there. So T becomes TD when the total effective thickness is there. So that's why here directly it's a TD, and this already we had seen this equation also in our previous video. So TDX into DS plus R equals to 1 to N BR XR minus this term Sy, comma 0 minus of Sx, comma 0 minus I into Ix by Ixx Iyy minus I square xy. That again is common. Then again another term is 0 to S TD Y. Here x dx was there, here y ds. So x ds and here y ds. Here r equals to 1 to n BR XR, similarly plus r equals to 1 to n BR y bar. So simply from the same equation, just replace wherever x is there to y for this one, and 1 to 0 or 0 to 1. Now for q1 will be what? Whatever is here. So 0, wherever 0 is there, just replace 0. Remaining everything will be same. So just see here. q1 equals to minus of sx comma 1 ixx minus sy comma 1 ixy by ixx into iyy minus I square xy whole, that is this part is the common. Similarly like this again 0 to s tx tdx ds plus sigma r equals to 1 to n br xr. So this is the x part. So that's why br xr. Now for y, so s y comma 1 into ix iyy minus s x comma 1 ixy by ixx into iyy minus I square xy. This part common, then whole in that into 0 integral of 0 to s td. Now x becomes again x replaced to y here because this is for y term into ds plus r equals to 1 to n br yr. So this will be for the q1. Now just substitute these two here, and then just like last equation, multiply, expand, put ixy comma that ixy equals to 0 and then simplify. Then what you will get? Similar to this expression. So delta s will be here. Okay. Now, so this topic over. So now next topic is thin walled rectangular section beam subjected to torsion. So now what is there? Because just see, till that what we had seen, torsion is not there. The load is acting at the shear center. If that load is not acting at the center, then what we did for that one? Just again replace that load acting other than the shear center, take off the torque and the same load at the shear center. So now just add both, and that force also will be, or that load at also will be the shear center. Okay. So now if that is not there, then what happens? So just here, a closed section, right? Or that you can say that open section also the same way will be there. Open section or closed section beam subjected to a pure torque T as shown here, right? In figure, this one does not, in the absence of axial constraint, develop a direct stress system. So if that stress direction is not there, right, then it will not, what, that does not have the torque in the absence of axial constraint. Just we had seen if that should be at the axis, that shear center, then only that will be 0. Otherwise, it won't be in equilibrium. So it follows that the equilibrium condition reduces to what? Delta Qi delta S equals to 0 and delta Qi delta Z. So just see here, this is for delta S and this is for delta Z. That is equals to 0 respectively. Now just use this one, and so after that, even this becomes more simpler. This relationship may only be satisfied simultaneously by a constant value of Q. So now here what happens? This will satisfy when Q is constant. That may only be satisfied simultaneously by a constant value of Q. So it's the same. We deduce therefore that the application of a pure torque to a closed section beam result in the development of a constant shear flow in the beam. So just see here why this Q is there. So therefore the application of pure torque, if only the torque is there, that here itself that is mentioned, that pure torque is there. So for pure torque, what happened to a closed or open section beam result in development. So because of the pure torque, a constant shear flow will develop on the beam wall. Now just here. So this is for torsion of the closed wall, and here the how the shear stress distribution will be there. So shear flow distribution in a closed section beam subjected to torsion. When torsion will be there, then how the shear flow distribution will be there. That is that. Okay. So, however, the shear stress tau may vary around the cross section since we allow the wall thickness T to be function of S. Why? Because T is the function of S. As T is changing, but S is changing, T will change, right? So we can say that tau may be vary around the cross section. It depends, that simply tau depends on the cross section area of that one. Whatever the cross section will be there based on that one. The relationship between the applied torque and this constant shear flow is simply derived by considering the torsional equilibrium of the section shown in figure 2. So already we had seen with the same that we will use. Now what will be the torque? The torque produced by the shear flow acting on an element delta x. So where it's acting on the element delta x of the beam wall is PQ delta S. So where it will act? PQ is this one. So the torque will be force into Q into delta S, right? So that will give you the torque. So now torque will be what? Total integral that for the closed cycle that is there for the closed one, right? So if it's a open one, then this circle won't be there. Just we have to. So T equals to closed integral of PQ ds. Or since Q is constant, then what happen? Q we can take out of the integration, so that becomes closed integral of P ds. So now what is that? And P closed integral of P ds is equals to what? 2a. So just substitute here. So what we have, T equals to, after taking, because Q is constant, so taking out of the integral, closed integral of P ds. So Q into what is closed integral of P ds, that is equals to 2a. So 2a. Hence T equals to 2aq. So now torsion will be 2aq. Okay. Note that the origin O of the axis in the figure 2 may be positioned in or outside the cross section of the beam, since the moment of the internal shear flow whose resultant is the pure torque is the same about any point in that plane. So in that plane, whatever is there, that shear flow will be uniform, right? So that can be either inside or outside, that doesn't affect, right? For an origin outside, just see how outside will be there, then what happened? For an origin outside the cross section, the term PDS will involve the summation of positive and negative areas. So this PDF will give that positive area is there or negative area is there. The sign of area is determined by the sign of P, which itself is associated with the sign convention for torque as follows. So just see how that it depends on P, that area will be negative or positive, because PDS is the area. So if P is negative, area will be negative. P is positive, area will be positive. So how we will determine that? According to the torque, whatever torque is there. Now, how to find that torque is positive and negative? That is here. So just say, if the movement of the foot of P along the tangent at any point in the positive direction of S leads to anti-clockwise rotation of P. So along, if that foot of the P is tangent to point and in the positive direction of S, right? And positive direction of S means it's anti-clockwise. So if it's rotating in anti-clockwise, then what happens? Then that we can say that is the positive. So P is positive, means if anti-clockwise, then P is positive. The positive direction of S is in the positive direction of Q, which anti-clockwise corresponding to a positive torque. So Q is also positive and S is also positive in anti-clockwise direction, hence torque also will be positive. Thus in figure 3, a generator OA rotating about O will initially sweep out a negative area since P is negative. So just see in figure 3 here, that O, right? So this O, yeah, sorry, actually this is in figure 5, not here, figure 3. Figure 5A, that generator OA rotating about O will initially sweep out a negative. Just to see here in 5A. So this is OA. So means this part first from here. This is the generator, right? So now it's generating the area. So this part will be what? Negative. So in starting it will generate first negative part and then it will generate here as the positive area. Okay. At B, once this will reach here, however PB is positive, so that the area swept out by the generator has changed sign. So from negative to that becomes positive at the point where the tangent passes through O and P equals to 0. So where P equals to 0 is there and tangent passes to that one, there that will be 0. So now here that tangent is passing at point B. So hence the sign got changed. Positive and negative area cancel each other out as they overlap, so that as the generator moves completely around the section. So just see, it's completing the whole, right? So negative area and positive area, that will get cancelled out. Okay. Okay. Say 2A, say the resultant area is that enclosed by the profile of the beam. So whatever that enclosed area will be there, that will be the profile of the beam. Okay. So here, this is the reference that again Maxon book is there. So you can go through that book. If suppose you have any doubt still, you can just ask in the comment itself, or you can contact me directly to clarify your doubts. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.